of the slides quite quick. Almost the same agenda: background, summary, data preparation and feature engineering, training methods, public leaderboard fitting, and finally simple model. Background: I have studied quite a lot and I have several degrees, but of relevance to this competition is a master in statistics. I have a varied professional background, ran my own company for many years, and I have done a lot of other things. But for the last 5 years, my income comes from financial assets trading with my own private capital. And I have participated in 7 Kaggle competitions before this one, with the incentive to develop my data science and statistical skills. And I have learned a lot from all of them, and it was a lot of fun. Okay, model summary. Overall, I would describe it as a straightforward approach. 5 split cross-validation, data augmentation. I will get back to the data augmentation in a separate slide. I use no additional offline generated training data and no feature selection, at least no feature selection to speak of. And the overall model consisted of a weighted ensemble of 7 models, whereof 4 boosting and 3 neural networks. And the final submission used an equally weighted mix of 6 full sets of models, where the used seed for training was the only difference. And total training time was less than 3 days on one machine. And I actually had 2 final submissions, one cross-validation based approach and another one almost exactly the same, using the same trained models, but with some additional weighting based fitted directly from the public leaderboard. I get back to that as well. Okay, data preparation and feature engineering. I start with the data augmentation, which I think was the single most important data preparation and feature engineering I did. And after the competition, I saw that several other teams used exactly the same augmentation, which did not surprise me because I think it was, given the data, a quite natural approach. What I did was that I looked at the data and I saw that for the Monte-Carlo tree search algorithm settings, when agent 1 had certain specifications for a certain game and agent 2 had others, in the data, the inverse was not present with flipped agents. So I thought, what if we just flip the agents? Well, if we flip the agents, then probably we should also flip the target, because if agent 1 performed well, then yes. So sign flipping of the target seemed reasonable, and if we flip the agent settings and we flip the target, then probably we should flip this important variable advantage player 1, which doesn't seem to perfectly capture the play imbalance in the game, but it still gives quite a lot of information. And flipping this variable would be taking 1 minus the value, because the range of advantage player 1 was between 0 and 1. And then we come up with some kind of upside down version of the game, or mirror version or something, which is this augmentation is by no means perfect, I would say. But on the other hand, the idea of augmentation is not to make an absolutely perfect representation, because then we don't add anything, or at least don't add much. But it should be, the augmentation should add something which hopefully improves the model performance. And this significantly improved both cross-validation and public leaderboard score. And I also added an augmented data dummy feature to let the models know which rows of data that originated from augmentation. And finally, I also used augmentation in inference. So all the models were trained on both the original data set and the augmented set. And at inference, I made 2 predictions, one from the original test data and one from the augmentation modified test data. Other data preparation and feature engineering, I will go through this quick because I don't think it's that interesting. Dropped duplicate and non-information features, calculated text scores features from the LUD rules column, and I want to thank Kaggle profile Yunsu Xiao Tzi for this idea. I didn't come up with this myself. I sorted data in groups created from the LUD rules column by TF-IDF vectorization and k-means clustering, thus reducing the number of rule sets. And the reasoning behind this was to make cross-validation estimates that hopefully generalize better outside the training data if similar games were grouped together in the same fold. And I think this, I don't have any numbers, but I'm pretty sure this improved the performance a little bit. I also dummy encoded unique rule sets from the LUD rules column. These were not used in the neural network models because it didn't seem to improve performance, but it seemed to slightly make the boosting models generalize better. So I trained half of the boosting models with this approximately 1,400 extra dummies. Then I dropped the rules columns and ID, used data augmentation as discussed in previous slide. I one-hot encoded the agent specification category of features with the most common value used as baseline. So in the training data, there were only dummy features and continuous variables. And the continuous variables were mapped to standard normal distributions before training of an inference from the neural network models. Here's a feature importance plot from a CatBoost model trained on all the data. I'm not going to comment this much, except that there's a lot of these agent settings dummy features present in the top 20 features, which is nice to see because sometimes when I was doing this competition, I was thinking, oh, are we mainly just predicting the game characteristics and not so much the performance of the different algorithm settings. But as you can see, it seems that they play quite a big role actually, which is nice to see, I think. And this is extended flipped feature here. That's my augmented data dummy. And I think this indicates the non-perfectness, if you will, of the data augmentation that is quite important in the model. Here's a partial dependence plot of the Advantage Player 1, also from a CatBoost model trained with all of the data. It looks like could be expected, almost strictly increasing. Training methods. The overall submission was an ensemble of 7 models, 4 boosting models and 3 neural network models. The boosting models trained with and without the dummy rule set identifiers. And I then weighted these 7 models using out-of-fold predictions and an ordinary least squares regression. And to not get too many parameters to fit and in the regression, I first blended the boosting model predictions with 50-50 blends of the dummy rule with the models trained with the 1,400-ish dummy rule set, extra dummies and without. And then I blended the CatBoost and the LightGBM models with an 80-20 blend. I probably could have gone with just CatBoost and skipped the LightGBMs, but because they didn't seem to add much, not in cross-validation scores and not in the public leaderboard. But I used to include them with 20%, hopefully, with hope that they would generalize better. And these blended boosted predictions came in 2 versions, one using the original test data and one using the augmented modified test data. And then 3 neural network models, a standard multi-layer perceptron, a second just bigger multi-layer perceptron, and finally an autoencoder followed by multi-layer perception. And the outputs from the neural networks were used directly in the least squares weighting. And here are just the weighting estimates. You can ignore the p-values and confidence intervals because aside from selection bias, etc., the data is of course also heavily clustered in the different games. But it shows that the boosting models of big importance, the augmented predictions from the boosting models, big importance. The negative sign here is just because negative sign were expected for the augmented predictions. And the first neural model, important and unexpected for me at least, was that the bigger multi-layer perception and the autoencoder gave negative ensemble estimates. Generally, I'm quite skeptical to negative weighting, but it improved both the cross-validation and public leaderboard scores. So I decided to keep them. And probably it's just because they're overfitting, but I think with more time, I probably could just adjust the settings and get positive estimates and maybe a better model. And I also included Advantage Play 1 with a minor weighting. I don't think it did much, but maybe it reduced overfitting a little bit or something. And then I kept the ensemble prediction to the target range and scaled them again as slightly linear upscaling, and then finally kept the final predictions. That was what I just described. That was my cross-validation approach. And then I also did a public leaderboard fitting approach, which was identical, but with two differences. In the public leaderboard fitted approach, I also included augmented data predictions from the neural network models. And they got negative weights, which I fitted directly from the public leaderboard. And secondly, I also include a prediction set with equal weights to all model predictions, but sign flipped were expected. That is the augmented data predictions. And these total set predictions were then added with, again, negative weights fitted directly from the public leaderboard. And I interpreted this, when I did it towards the end of the competition, I interpreted this as a almost desperate, obvious public leaderboard overfitting approach. But of course, it improved the public leaderboard score since the weighting was fitted from the public leaderboard, but it also improved the private score. And after the end of the competition, there were some complaints regarding the private test set, and I think that's to be expected in almost every competition, that there will be complaints about the constitution of the private test set. And I do think that my cross-validation based submission would get a fairly decent ranking among other cross-validation based submissions. But still, I do think that I also want to say that I absolutely understand the host's argument why they choose to constitute the private test set as they did. But I still think more generally speaking, I think there is some credit to the argument that ideally there should not be a much stronger alignment between the private test set and the public test set than between, say, the training data and the public test set, or for that matter, the training data and the public test set. Yeah, I just want to mention that. And finally, a simple model. I go through this very quick because I have this gut feeling that I'm over my time. I first had a simple model with the top 10 features. It performed really badly, so I extended it to the top 20, including the most important agent settings. And a single CatBoost model trained on all the training data with top 20 features gave a private score of 0.48 compared to around 0.42 for my second place winning model. And given that this single model only used 20 features and one model compared to this kind of monstrous total model numbers for my winning submission, I think it's a decent score. And for comparison, I also added an ultra simple, just linear fit using the Advantage Play 1 column alone, and that would give a private score of 0.55. Okay, thank you.